Welcome to lesson 5 of unit 6. It's our last lesson of this unit, so that is very exciting. So just kind of a couple quick notes. This one is all about solving equations, as we've been focusing on graphing for the last couple. This should seem relatively familiar in the sense that you have seen solving radical and rational functions before in grade 11, but just kind of as a quick recap because it does show up on the provincial. So looking at this first example, we're solving the equations algebraically. So we've got two options. We can solve algebraically or graphically. So again, algebraically is our first set of examples. When you are dealing with radicals, you want to make sure that as much as possible you get them alone if there's only one radical. So just kind of as a quick note on that front. One radical equals isolate. Okay, so in this case, I would start by needing to move this positive 1 onto the other side. So I would end up with the square root of 3x minus 1 equals, and then 2 minus 1 is 1. Once I've got my radical isolated, now I can undo it by doing my opposite operation, which in the case of square rooting is squaring it. So I'm going to square both sides. That leaves me with 3x minus 1 equals 1. Once I have this, it's just like solving any other linear equation, which you've been doing since at least grade 10, hopefully before that. And we've got 3x equals 2. Or x equals 2/3. Now, the only tricky thing to note here is that we are going to have some non-permissible values, and we can't forget those. So we do need to write those down and double check that this solution fits. So in this case of radicals, remembering that we do have some restrictions on our domain because I can't take the square root of negative numbers. So 3x minus 1, that piece that was from underneath my radical, needs to be bigger than or equal to 0. It can't be negative. Okay, so I'm going to determine my non-permissible values by moving that 1 and 3, and that gives me 1/3. So x must be bigger than positive 1/3. Because my solution fits this domain restriction, it does work, and it is a solution. Yay! For example B, we see that we've got radicals on both sides, but what's nice here is that we don't have any other pieces. There's nothing outside the radicals other than other radicals, so we don't need to worry about rearranging it all. So it still works out nicely. I'm still going to square both sides right away. And that leaves me with 2x plus 3 equals 4x minus 1. From here, collect like terms, isolate your variable. So we've got 2x equals 4, x equals 2. And that's great, but I still need to check my non-permissible values for both. So my first one, 2x plus 3 needs to be greater than or equal to 0. But I also need to bear in mind that 4x minus 1 needs to be greater than or equal to 0. And whichever one of these gives us kind of like the more defined restriction is the one we're going to work with, or we might need to consider both. So working on the left, x needs to be greater than or equal to negative 3/2. With the right-hand side, we've got x needs to be greater than or equal to 1/4. So it's a greater than in both situations, but if I look at my number line, and I've got -2, -1, 0, and 1. If I plot this domain, it says greater than -3/2. So greater than or equal to here would be my kind of graphic description of it. But if I'm showing you, I'll use a very distinct color, blue, greater than or equal to 1/4, that's over here. And so because of that further restriction, even though these values would work on the left-hand side, they wouldn't work on the right-hand side. So my actual non-permissible value, or my domain for this, is going to be the one that restricts it more. 2 is still a valid answer, good to go, but my non-permissible value, or my domain, would be starting at at 1/4 and going to positive infinity. Okay, so even though this is true of the left-hand side, because the right-hand side is more restricted, that is what we have to contend with. All right. When dealing with rational equations, if you recall, we want to get rid of the denominator. We need to get everything out of the denominator. So what we're going to do is we're going to multiply by all of our denominators so that they go away. So my lowest common denominator, or my lowest common denominator, is going to be x minus 1, times x plus 4. So I'm going to multiply all of my terms by this set of binomials. So you can take the time to rewrite it out if that's something that you need to do. I'm going to do it for this one just so that you see what it looks like. But when we're multiplying it out, we're multiplying in the numerator. So what we're doing is we're going x minus 1, x plus 4. Then I need to multiply the next term by the same thing, x minus 1, x plus 4 equals, and I need to do the same thing to each term on the other side. X minus 1, x plus 4. Okay, so again, I'm multiplying by my lowest common denominator each term. And what that allows me to do is it allows me to go through and get rid of my denominators, because x minus 1 cancels out here, x plus 4 cancels out here, and it leaves me with some numbers that are a little bit more manageable, because at least they're in the numerator. Because as we all know, fractions are one of the F words in math. You just hate it when they get said, when you see them on a page. So many people cringe. It's just not a positive reaction. So what I'm left with is 3 times x plus 4, so I can distribute that in. I've got 3x plus 4 plus, I'm going to have a quadratic that I'm then going to have to distribute this 2 into. So if you want to pause, go ahead. I'm going to end up with 3x, 6x minus 4 minus 8 equals, and then I'm only left with this binomial here, so that's 2x minus 2 once I distribute in there. Okay, now I get to collect like terms, and because I'm working with a quadratic in this case, as opposed to my linear equations that I ended up with up here, which were nice and simple, quadratics, we always want to get everything onto the left and solve for our zeros or our roots or our x-intercepts, whichever word you're inclined to remember what to do with. I like zeros just because that's really what it is that we're looking for in this particular case. So we're going to move everything to the left or the right, whichever one you want, but get everything on one side and get it equal to 0. So if you want to pause right now and practice that, you're more than welcome to. I'm going to end up with 2x squared. 3 and 6 is 9, minus 2 is 7x. And then 4 minus 8 is negative 4, plus 2 is negative 2. Okay, now unfortunately, this is not factorable, and so I would need to use my quadratic equation. If you don't remember that, don't worry. I'm pretty sure if I go into our general info formula sheet, our quadratic formula is right there. Yay! So that'll be useful to have when we are doing this on the provincial exam and you run into a situation like this. So I can't factor it, which means I'm dealing with solving for x this way. And I'm going to do it by going negative b, and b is 7. So just as a quick refresher, a value, b value, c value, negative b plus or minus the square root of b squared, so 49, minus 4 times a times c, so that's times negative 4. If I multiply those two together, divided by 2a, so it's also 4. So it's 49 plus another 16, 59, 65. And if this is on the non-calculator section of the exam, this is what we leave it as. The only thing we have to remember, don't forget, is that our non-permissible values are when my denominator is equal to 0. So x can minus 1 cannot be 0, or denominator can't be 0, whichever way you want to think about it. X plus 4 cannot be 0. So x cannot be 1 and x cannot be negative 4. Good news is that neither of these numbers are negative 4 or positive 1 because we got some weird funky radicals going on in there. So x can be both of these. Those are both valid solutions. Okay. If we are solving things graphically, we're going to treat them as if they're two separate functions. So I could call this f of x equals the square root of 2x plus 1, and g of x equals 2x plus 1. So if I go to graph this, well, this one's going to be nice. It's going to be a straight line. This one's not going to be quite so nice as it is a radical. So I can figure out my non-permissible value or my starting point, my domain restriction, by setting this up. 2x plus 1 has to be bigger than or equal to 0. So x has to be bigger than or equal to negative 1/2. So in terms of setting up my scale, I'm pretty flexible on that front. I might even do negative 1 there. Okay, making sure I name my axes. It's a little spread out. Okay, and so when I'm starting at 1/2, you can make a table of values. You can use your knowledge of transformations. Okay, so my next one, if I was using my original function of just square root of x, would be 1 and 1, but I've shifted around a little bit. I'm just going to plug in some values and mentally do it. So I'm going to go 0 times 2 is 0 plus 1. Here. Okay, if I do 1, then that gets me 1 times 2 is 2 plus 1 is 3. So square root of 3, which is a little weird. Maybe if I go to 2, 2 times 2 is, or if I go to 1 1/2 times 2, that's 3 plus 1 is 4. Square root of that is 2. So that gives me a nice point there. So that gives me a couple points to work with. Okay. Then I've got my line, 2x plus 1. So my y-intercept is here. And I'm just going to graph this one in purple so that we can keep track. And it increases by 2, rise over run. So rise is up 2, run is 1. So my next point is way up here. Conversely, down 2 and over 1 is over here. So we get this interesting line going on where we actually are going to have 2 intercepts. Showing, and those 2 intercepts are our 2 solutions. Okay, so answers are going to be, and again, we're only solving for x. There's no y here. So x equals -1/2 and 0. Okay, so again, no y. Because it's not in our equation. These guys get a little bit more complicated. So we're still going to do them graphically. We're still going to treat them as 2 separate functions. So I'm going to have f of x be my left-hand side, because just default to that. X squared minus 10x plus 25 over x minus 5. Now I'm going to do all my rational graphing stuff with this before I even look at my next equation. So I'm going to look at factoring my numerator, which gets me x minus 5 squared over x minus 5. And so that simplifies to just x minus 5. But I need to remember that there's a whole at x equals positive 5 because of that denominator. Okay, but straight line works out nicely. G of x, I'll just make this a little less fat so it's easier to read, is going to be my right-hand side, so that's x plus 1 divided by x squared minus 4x minus 5. And we see that we can factor this denominator. Minus 5 x plus 1, and it nicely cancels out. So that leaves me with 1 over x minus 5. So I'm going to have an asymptote at x equals 5, and I'm going to have a whole at x equals -1. Okay. Once I have all of this information, now I can graph it. I know I need to go up to 5 in terms of my x values. I can kind of use this as a gauge because there's no slope. I'm going to have to go pretty wide though. So I'm going to make my scale pretty big in comparison to the last one, which we were really zoomed in on. So I'm going to go, each one of these ticks is going to be worth 5, or 1, sorry, so that I can get all the way up to 5, no problem. Sorry if this is a lot of dead space. Feel free to skip my graph scale drawing. Scratchy voice. Okay, so I've got my scale labeled, I've got my lines drawn in, so I'm going to draw f of x first. I've got my axes named. So I'm going to draw a line starting at -5, slope of 1, so it's going to cross here at +5. Okay, but it's going to have a hole there, so being careful to be conscious of that, and especially with, again, this stylus not being my best friend on the surface. There must be, I'm sure there's a setting where I can choose to not erase everything at once. Okay, so that is f of x. Okay, g of x, I know I have an asymptote here at positive 5. Okay, I'm going to have a hole at negative 1. And from there, I can figure out some values. If I plug in negative 1 here, I can find out that that's going to be negative 6. So negative 1 and negative a 6, that's going to be a hole. Okay, if I plug in 0, it's negative a 5th. It's pretty close in there as well. Okay, but it's only over at like positive 4 minus 1. That's going to get me to negative 1. So just to get that point in there. And so you see it that we're crossing our graph at that particular place. Okay, and then it curves downward from there. Okay, alternately on the other side, positive 6 minus 5 is 1. Get to my other point that's going to end up being my intersection. So we see that our final solutions are here and here. But again, there's no y. So my answers are that x equals 4 and 6, just looking at my x values from the points of intersection. Okay, and that's the end of our lesson. That's the end of our unit. So work on homework questions, practice questions. Any quests that get posted in the next little bit will strictly be for practice. I won't count them for marks. Just so that you are getting that practice in and that feedback. But because I know we're crunched for time, I'm not going to say like, oh, these absolutely must be done by this date for marks. I don't think that that would be a fair thing to do. So use them as practice, as feedback, but don't worry about the mark that comes out of them. Okay, and as always, if you have questions, ask.